This animation will demonstrate how orbital mechanics can defy our preconceived notions about motion. Before we can fully comprehend how, let's go over some basic concepts: what mechanical energy is, why orbiting is necessary to stay in space, and an overview of orbital maneuvers. Next, we will examine why we must slow down to travel faster and speed up to travel slower when navigating in an orbit. To begin with, what constitutes an orbit? Is it simply the distance from the surface of the Earth? That is, if we position the SpaceX crew, if we give Dragon capsules some horizontal velocity, represented by the red arrow, the trajectory starts to change, and if you move fast enough horizontally, the spacecraft will never hit Earth. However, if the Dragon capsules are hundreds of kilometers above Earth and are not subject to gravity, as indicated by the blue arrow, they will pull on them, follow the trajectory of this blue line, and fall out of the sky towards Earth. The rocket must reach these high velocities in order to enter orbit, which is only possible in the absence of air resistance. The spacecraft needs kinetic and potential energy to reach a high enough altitude to escape the dense atmosphere. These factors are determined by the spacecraft's speed and altitude. Potential energy derived from its height or altitude, and kinetic energy from its speed. This formula can be used to calculate mechanical energy, which is the sum of these two types of energy. A roller coaster is a fantastic mechanism to demonstrate mechanical energy. A roller coaster train's mechanical energy will never change, but it will constantly exchange kinetic energy for both potential energy and the opposite. It slows down, decreasing its kinetic energy but increasing its gravitational potential energy, depending on where it is on the track, and the opposite is true as it descends towards Earth. If the orbiting altitude remains constant, an orbit that is perfectly circular will have constant kinetic and potential energy during each orbital period. However, orbits are never perfectly circular, therefore they are elliptic. The point closest to the orbiting body is found in an elliptical orbit. It's known as the periapsis, and the apoapsis, which is the point at which the orbital height is at its greatest distance from its orbiting body. The perigee and apogee are the names given to these 2 points when discussing a spacecraft in orbit around the Earth. Rearranging your orbit's size, shape, and angle is a major part of learning orbital mechanics. Let's take a quick look at the various orbit manipulation techniques to finally comprehend why we must slow down our spacecraft in order to accelerate to slow down. The prograde and retrograde burns are the most frequently used types. Burns whose burn vectors are parallel to the direction of motion are referred to as retrograde and prograde burns. Let's examine a particular illustration of each. When you fire your engines in the direction you came from, it is known as a prograde burn. Your velocity or kinetic energy will increase during a prograde burn, but not your altitude or potential energy at that particular moment. However, as you continue in your orbit with increased kinetic energy, your inertia will make the centrifugal force pushing outward from you greater than the force of gravity, causing you to gradually descend farther and farther from Earth. Your orbit will now be elliptic and appear like this as you ascend in altitude. Peruse that once more. Because of the increased inertia and slightly stronger centrifugal force, you are able to resist gravity to a slightly greater extent, which causes you to fall away from Earth. It is very similar to a retrograde burn, which would occur if we fired our engines in the opposite direction. It therefore deducts kinetic energy from the orbit at the point where you fired your engines, leading to a prograde burn in the exact opposite direction. This affects the altitude of the opposite side of your orbit, bringing it closer to Earth. Now, instead of doing a professional grade burn, could you just fire your engines at Earth to raise the altitude of your orbit? Let's try it and see what occurs. It is referred to as a radial outburn. During a radial outburst, your spacecraft will be able to withstand the effects of gravity to some extent, keeping a more straight path during the burn, but you slow down as you ascend above Earth because your orbit doesn't gain velocity. The opposite side of your orbit will be drawn closer to Earth as a result. The end effect is that you don't gain much energy as your orbit revolves around your spacecraft. The final burn types that can be made are normal and anti-normal burns. A radial inburn in which you launch your rockets into space will have the same effect, but in reverse. When you finish a normal burn, a normal anti-normal burn is perpendicular to your direction of motion. Your rocket starts to ascend higher than your starting orbit. But since you are still in orbit around the planet, your orbit will continue to slowly rotate, with the planet as its center of rotation. This maneuver, known as an inclination change, involves a significant amount of fuel. Usually, they are only applied for adjustments when aligning with another spacecraft's orbit. Following our review of the fundamentals of spacecraft mechanics, let's attempt to navigate an orbit using what we've learned. Here's a real-world illustration: a SpaceX Dragon capsule making a rendezvous with the International Space Station. Assume that you and the ISS are in the same orbit. It makes sense that, with it directly in front of us, we should fire our rockets from behind to get a closer look, a pro-level burn. I'll watch how this changes your orbit around the International Space Station. Because of its increased kinetic energy, the spacecraft will be pulled away from Earth faster than Earth gravity can pull it in. This is known as the outward centrifugal force. Return to it. As a result, the rocket loses kinetic energy and gains altitude or potential energy, operating similarly to a roller coaster on an incline in a track. The spacecraft loses kinetic energy as a result of this gain and potential energy. Since our new orbit is higher in the sky, its average speed is now slower. The Moon's orbit, which takes 1 month to complete around the Earth, is an excellent illustration of this slower and higher orbit. The spacecraft will rise above the International Space Station and descend further if we track its position in relation to the station, because of this extended orbital period behind. But what if we take the exact opposite action? To see what happens, let's try firing our rockets in the direction we are traveling in, which will slow us down with a retrograde burn. Our kinetic energy will decrease if we fire our rockets in this direction, but our potential energy will not change. As we orbit, the spacecraft will be drawn closer to Earth by the decreasing kinetic energy more quickly than it will be pulled away by inertia. Energy will be exchanged as a result of this. If we trace the orbit's path in relation to the ISS, we will get closer to it as we pass under it, converting potential energy into kinetic energy. This only leaves us with one issue. At one point during our apoapsis, we are on the same orbit as the ISS. It will now take one more prograde burn to circularize the orbit and imitate the ISS's orbit.